Today we're going to look at the implications of the solution of the Schrodinger equation for the hydrogen atom. In my earlier video, I showed how we moved from the Schrodinger equation to its solution for the hydrogen atom. The full Schrodinger equation that has to be used is minus h bar squared over 2m times d2 psi by dx squared plus d2 psi by dy squared plus d2 psi by dz squared plus the Coulomb term ze squared over 4 pi epsilon naught r psi equals e psi. I pointed out that that was a very difficult term to solve, but that we would do a cheat solution. And we ended up with a formula that said that E, energy, equals minus me to the fourth over 8 epsilon naught squared h squared times z squared over n squared. And I pointed out that this term is just made up of constants and can be reduced to a single constant, the Rydberg constant. And so this becomes minus r times z squared over n squared. The Rydberg constant has a value of 13.6 electron volts. This, I explained, meant that the energy of the electron in a hydrogen atom is constrained by this formula. The electron can only have the energy given by the formula. Since in a hydrogen atom Z equals 1, because there is only one proton, the energy levels are governed by the integer values. So when n equals 1, the energy of the electron is minus 13.6 electron volts. When n is 2, the energy of the electron is 3.4 electron volts. Let's not worry about calculating how many electron volts the electron has. Let's just look at the proportions. We go back again to n equals 1, that's 13.6 electron volts. When n is 2, the electron energy is only a quarter of that. When n is 3, the electron energy is only a ninth of that, because it's 1 over n squared. When n is 4, it's only 1/16 of that. When n is infinity, the energy is 0, and that means that the electron can escape the hydrogen atom. It is no longer bound. All these negative terms mean that the electron is bound to the hydrogen atom, and you have to give the electron energy if you want to get it out. That means to get an electron to go from that energy to that energy, you have to give it energy, whereas if an electron falls from that energy to that energy, it gives up energy. So what is quantum mechanics telling us? And more specifically, what is the solution to the Schrodinger equation telling us? It is saying that the energy levels of an electron in a hydrogen atom are constrained to be only these. An electron cannot, for example, have an energy here. That is not allowed. But how does an electron change energy levels? Well, the answer is it either has to receive energy if it's going to move up the energy level, or it has to give off energy if it moves down. Where does this energy come from? It comes from photons. What happens is an incoming photon hits the electron and transfers its energy in total to the electron, and the electron moves up to the next energy level. But it will only do that if the photon has precisely the amount of energy that is represented by the difference between these two energy levels. If the photon does not have that precise energy difference, the electron cannot move, because it cannot move here or here. It has to go precisely to the next level. If the electron drops down from this level to this level, then it will emit a photon, and that photon will have a very precise energy, because the energy will be precisely the difference between the higher energy level and the lower one. But we know that that energy is given by h, Planck's constant, times f, the frequency. And therefore the frequency of that photon will be very precise indeed. At this point, you may be wondering how we can possibly know any of this, and whether any of it is susceptible to experiment. And the answer is, it is susceptible to one of the easiest experiments of all time. Indeed, the experiment had already been done when this work was done by Schrodinger, so it was very easy to demonstrate that this solution was right. The experiment is very simple. You take a glass tube, you evacuate it, you fill it with a small amount of hydrogen, and you pass an electric current through the tube. This makes the hydrogen glow. You pass the light that comes from that glow through a prism. A prism has the effect of splitting up the light into its constituent colours. Different frequencies go through the prism at different angles, and so the light is split up. When you do this with hydrogen, you find that you get 4 very distinct lines. One of them is red, one is green, one is blue, and one is violet. We know the frequencies of those 4 lines, and consequently we can calculate E equals hf, Planck's constant, times the frequency. And guess what? The red line precisely corresponds to the energy difference between n equals 3 and n equals 2. The green line precisely corresponds to the energy gap n equals 4 and n equals 2. The blue line precisely corresponds to the energy gap between n equals 5 and n equals 2. And the violet line precisely corresponds to the energy gap between n equals 6 and n equals 2. But, I hear you say, what about an electron that falls down to n equals 1? Surely that would give off some photons as well. Why do we not see those in the spectrum of hydrogen? And the answer is that only the 4 jumps from n equals 6 to n equals 2, or 5 to 2, or 4 to 2, or 3 to 2, produce photons in the visible spectrum. Any jump to n equals 1 will be a much higher energy than that, and that means that it will be in the ultraviolet region. Similarly, any jumps at higher levels, for example from n equals 9 to n equals 8, will be very low energy level jumps, and they will be visible only in the infrared spectrum. We cannot see with our eyes ultraviolet or infrared, but if you get an ultraviolet detector or an infrared camera, then these lines become visible. And so the spectrum of the hydrogen gas gives us the proof that we need that the Schrodinger equation gives us a solution for the energies. And it also gives us the reason why electrons cannot spiral into the nucleus. They are constrained to operate in fixed energy levels. They cannot go into ones between. They cannot spiral. They can only move from one energy level to another, and that is by either by receiving energy at a particular frequency or by giving off energy at a particular frequency. Finally, this explains the photoelectric effect. The photoelectric effect says that when you shine light onto a metal, you might get electrons coming off, but only if you shine light at or above a particular threshold frequency. And now we see the reason. If you shine light at a frequency between the ground state and the E equals 0 state, then the electron might bobble about a bit, but it won't leave. You have got to supply an energy, which of course is represented by hf, that's big enough to get the electron out of the atom.